Previously on DOS.
The algorithm of second chance PRA is to make a FIFO great again, the clock PRA, and it's virtually identical to second chance. 3 hits, 13 misses. So in this example, it doesn't give us any advantage, but a better algorithm that is much more relevant is least recently used. This is the principle of locality. Pages that were recently accessed are more likely to be accessed in the near future. 4 hits, 12 misses. That's actually quite good, better than before, right? Not frequently used also. So it looks as if this algorithm was really good, but you can clearly see that it's not good. Let's take a look at aging PRA against simulations. 4 hits, 12 misses, so it performs similar to the other algorithms on this small example. Performance is quite nice over larger numbers. Every process has a working set size n. The n youngest pages are the working set. Okay, so let's see whether this algorithm was fair. We got 1 hit and 7 misses in the one process, 2 hits and 6 misses in the other process. Yeah, for our small example, maybe it's fair, but you should probably try that on larger numbers. 1C 13. And this means we have solved this example and it didn't take us very long. Then we see each other next week in the lecture and we will talk about scheduling.
Going till the dawn, C++ and Sun, System Level 101, operating systems done, far from where we started from, operating.
Welcome to today's lecture of operating systems. Today we will be talking about scheduling and deadlocks, and this is a very interesting topic. So let's start right away. Okay, I will just have to select the slides on my side so that I can also click on the next slide. Okay, let's start with scheduling. Scheduling, you all know scheduling probably. If I would ask you, okay, do you already know scheduling algorithms? Maybe you might say, oh, I don't know any scheduling algorithms right now. Maybe you know scheduling algorithms from the operating system's SWAP source code, round robin algorithm. But maybe you also know scheduling from some completely different context. And we've been all doing this all the time. Let's take a look at this schedule here that we have seen over years in school, right? Where we had different classes in school, Monday to Friday, and also at university to some degree. We still have these schedules where we have some classes at some time. And when we are in this situation with courses and or classes and schedules, then we usually also have some tasks to do, some homework to do, right? And maybe this is the first question that we want to start with today. Let me open this in the Menti. So if you haven't signed into the Menti yet, please do that. You can see the code up here, or you can find the link down here. And you can also, once you're at it, you can also click the subscribe button, because I'm still lacking 300 subscribers so that I can monetize this channel. And of course, this would be beneficial for everyone, I think. Okay, let's see. Let's open the Menti. And the first question that I have for you is which homework to do next. So you're confronted with the situation, maybe in school, but maybe also in university. You have several different homeworks for different classes. And which one do you do next? And what does it depend on, whether you do English homework first, or German homework first, or math homework first? The one that's due first, that's interesting. The hardest homework first. Okay, I have to go a bit closer as the font size is getting smaller and smaller. The hardest homework first. Okay. Deadline oriented, earliest required. Okay. The most easy one, yes, so that's also the less time consuming one. Yes. So there are different options here, and actually several of these that you have described here are actual scheduling algorithms that we are using in operating systems, as you will see on the next slide. So let's take a look at these scheduling algorithms. There's no right answer on which homework to start with, right? You know that from school, different students want to follow different approaches here. Some prefer the procrastination way, others prefer to get rid of the homework as fast as possible and then basically have a more calm state of mind afterwards. So there's no right answer. It's always a trade-off, and it's always depending on the preferences that you have in a situation, or the processes, if we're talking about operating systems, what the processes want, or what is best for the processes. Maybe they want something that is not best for them, but we will see. We had some ideas already, and I'm not sure, I didn't see it in the brainstorming, but I think it was there because it's quite intuitive. Oldest homework first. So once you get homework, you do it, and then it's done, and then the next homework that you got in, and so on and so on. That would be first in, first out. That's an algorithm that we just learned about when talking about swapping, right? There we also talked about first in, first out. But here it might make sense, right? The first job, and then it's done. We also know this as first come, first serve. And that's a principle that we use for scheduling in many places. For instance, if you go shopping and you queue at in the waiting line for the counter to pay for the items that you selected, then it's usually first come, first serve. The first that is there is served the first. Yeah, and these are used in the real world, also in technical contents, in operating systems, for instance. Then someone said, well, make it deadline oriented. The homework with the earliest deadline next. And that's actually also an algorithm that we use, earliest deadline first. Okay. If you want to maybe schedule it in a nicer way, at university it's often not possible to solve the entire homework of one class before starting with the homework of another class. Take, for instance, operating systems homework. To get the full assignment one done before working on any other of your tasks is not feasible. So probably you will schedule it more in slices, maybe 1 hour of this, then 1 hour of that, then 1 hour of something else. And this is also something that we know until everything is done. That's called round robin. Shortest homework first. We had this on the brainstorming slide as well. Shortest job first. We had this idea that we do the easiest tasks, the tasks that take less time. That was on the slide. And yeah, that's another algorithm that we can implement. But before we talk about these algorithms in more detail, we have to think about one more detail here. Are we talking about, like with homework, we are the one, the single core, basically, the single processor that can do the work, and we're scheduling things for ourselves. But what if we have a computer that doesn't have a single core, but that has many cores? Then scheduling also will change. But we first focus on the single core situation. Maybe also think about what could be good or bad for different situations. For instance, first in, first out. On a single core system, is it good or is it bad? What if we have a task that takes a lot of time on this single core machine? We will take a look at that in a second. Scheduling. Several of the design challenges that we have here are similar as with PRAs, with page replacement algorithms. We want to minimize the latency, we want to maximize the throughput, we want to maximize fairness and somehow measure what fairness actually means in this context. So several of these design principles are again applied here. And you might remember one thing from the last lecture and the lecture before that, that was the principle of locality. And just so that you have another reminder of what the principle of locality is, the principle of locality, we had this example where you have a tire blowout and a week after, and that is a week after hitting a side curb, and that's the principle of locality. Because that's the likely case that these two events are related to each other. And the more time passes between those two events, the less likely it is that these two events are related. So let's talk about some common terms, or define some common terms that we need when talking about scheduling. We will use the term task. That's basically anything that consumes time. We could also say thread here, a thread that does some work. And we've used this word already several times in this lecture. Latency, we also know the word latency. That's the time until a task is resolved in a situation, so until it's completely finished. And then we have predictability, also a word that you know. Here we talk about the predictability of runtime. How long will it take until the task gets scheduled, until the task is finished? So the predictability of the latency, for instance, also. Throughput, how many tasks can I get done over time, and how much time do I need overall? So there might be a scheduling algorithm where I need a lot of time for the same workload, where a different scheduling algorithm needs less time. And we will also talk about that in a second. Scheduling overhead. There is some overhead, and that's very closely related to the throughput question from before. How long does it take to switch from one task to another? Scheduling algorithms have to take that into account and want to minimize the overhead there if they can minimize it. Fairness, yes, of course, the above properties, but with respect to different tasks. You want to have a fair latency distribution. So there shouldn't be the situation that one thread has to wait much longer to be scheduled than another thread. The predictability should be fair. Throughput, you want each thread to make progress in a fair way. Scheduling overhead, throughput, yeah, again, you don't want to have one thread that always gets the larger scheduling overhead and all the other threads get lower scheduling overhead. That wouldn't be fair, right? And the worst part, starvation. If a task doesn't make any progress anymore because other tasks take away all the resources. For instance, because they say, oh, I'm more important and this other thread doesn't need to be scheduled. So a scheduling algorithm has to take into account all of that. It takes a workload or a task as an input, and then it decides which task to do first. Performance metrics like throughput, latency are also an output, and we only consider preemptive scheduling algorithms here. So other schedulers that are not preemptive, that are cooperative, are not considered here because they have much less flexibility. Preemptive schedulers are much more powerful. Yeah, maybe some more terms that we need to define. Scheduling algorithms should work well across a variety of environments, and that means that we want to apply the same algorithm on different kinds of machines, different hardware setups, different operating systems, designs. Even in systems that are not operating systems, maybe we have to implement a similar system also in some servers that have to schedule requests and decide which request to deal with first. So the workloads will vary from system to system and from user to user. Tasks can be either compute bound, that means they only or mostly use the CPU, they focus on the computation time, or I/O bound, and that would mean that most of the time they wait for I/O input. You probably have a nice example here from operating systems, from the web operating system. The shell, for instance, is an IO-bound task where most of the time you wait for input either from the user or for a process that you started to terminate. So most of the time the shell is waiting. A compute-bound task would be some process that does a lot of computations and nothing else, no IO. For instance, the mult-swep test program does a lot of computations, actually not that many computations, but a few computations, but no IO, so it would be more compute-bound. And then, of course, you can have mixed workloads where you have to compute a lot, but also want to get user input from time to time. And then this can be even more complex on how to schedule this in a nice way. Let's talk about the different algorithms that we already spoiled a bit in the beginning. So we talked about first in, first out, for example, which is like first come, first serve, and that we use a lot in the real world. You run the tasks in the order of arrival until either they complete or yield, until they basically say, I don't need to compute anymore right now. So using the yield syscall, for instance, they say, I'm done. First in, first out. Very short explanation, but the rest of that I want to discuss with you in a Menti slide that I prepared, and that's advantages and disadvantages. So what are the advantages of first in, first out? What are the disadvantages here? It's easy, yes, absolutely. Simple, yes. Low overhead, yes, that is also correct because we don't switch very often. High throughput, yes. It's also fair, right? It's fair if every task has to wait until it's their turn. Starvation, is starvation a problem? I mean, everybody waits their turn and then everybody will be served, right? After waiting their turn. For blocking tasks, this is bad. Okay, no multi-threading. Yeah, there might be some problems here. Congestion. What else do we have? What if no yield occurs? Okay. If long task is at a start. And that's exactly what I was waiting for, that someone points this out, that this might be a problem. There's a question in the Q&A. So task equals a thread. In general, I would say that a thread runs a task. So basically, that's the relation between thread and task. A thread runs a task. But the words are sometimes used also interchangeably. For instance, on Windows, you will see that the monitor to show you threads and processes is the task manager, and we'll also talk about stopping tasks, starting tasks. So yeah, sometimes they are used interchangeably, but the task could also be executed by a process, for instance. So I would say a task is something to work, some work that you have to do, and a thread is a construct that can perform a task. Okay. High latency, it might have a high latency, but actually we probably have to think about this a bit more, in which cases the latency is actually high. So let's move to the next slide. Yes, this is exactly the case that I wanted to talk about. And here we can see that a task 1, 2, 3, 4, 5, and this task takes a very long time, and the other 4 tasks are queuing up and they would need very little time, but they have to wait until this very, very slow and long task is finished. So yes, it's fair because everybody waits their turn, but it's not necessarily the algorithm that you want to implement, because it might be better. For instance, let's say this is the mouse movement that you want to draw on the screen. If you have to wait for some disk operation to complete until the user sees the mouse movement, then the user will not like that and will not like working with your operating system. So let's talk about a different strategy, one that was proposed by you on the first brainstorming. And that was, we start with the easiest task first, the shortest task. And while that can work with homework, you probably know that this is sometimes difficult to judge. It's difficult to estimate how long it will take. So is math homework less work, or is it English homework? I don't know. So which one do I start with? And then you start with one where you think, okay, it's very little time, but it turns out that it's actually a lot of time, but you didn't see that in advance. That's also a problem of this algorithm, shortest job first. You basically want to go the other extreme. First in, first out was optimized for throughput, right? We have very few context switches because every task finishes and then the other task is scheduled, so it's the minimal number of context switches. The other extreme would be optimizing for latency. So you always take the task that can complete the fastest. And that means that this one will observe a very low latency, and any task will observe a very low latency. But of course, tasks that take a long time, they inherently have a longer latency, but they also don't get much on top of that, right? So we optimize for the overall latency. Schedule the shortest job first. What would that look like if we take the previous picture with the 5 tasks? We would schedule it this way now. So we schedule task 2, 3, 4, and 5, and then task 1, which takes a long time. So let's talk about advantages and disadvantages for shortest job first. Let's see, what are advantages and disadvantages? How to estimate latency. Yes, how to estimate how long a job takes. No aging. A long task never gets done. Yes. Long jobs never finish. That might be the case. If I add too many short jobs, then the long job will never finish. Workload assumption. Yeah. We basically would have to assume things that we cannot know. Also, what about the latency, the fairness of the latency, or the predictability of the latency? What about this part? Is it still predictable? For first in, first out, it was very predictable because I know exactly that it's the amount that the previous task takes plus the amount that I need, right? Once I'm in the queue in, first out, I can estimate how long it will take. And then this might work in some setting where I know how long each task takes. Also, what about overheads? There's also no priority. Yes, maybe we want to define some priority. A lot of overhead, of course, if we always have to perform these context switches. Every time we get a new job in, then this will add a lot of latency because we are adding a lot of overhead. So the overall overhead of the scheduling will, the overall overhead will increase. But the biggest problem in your eyes is the long jobs never finish. Yes. high overhead, starvation for long tasks, high latency variance. Also, if you have a long job and it's already scheduled, but then it's interrupted and interrupted again and interrupted again, the long job never knows when it will finish. So this is a problem again, because the short jobs will always interrupt the longer jobs. And also another problem, in many cases we cannot even implement this because we don't know how long the tasks take. So let's go on to the next slide. And this is an example from the supermarket. Let's assume we organize a supermarket queue, a waiting line there at the counter, in shortest job first. So that means we don't have these Expresskassen and stuff anymore, but instead we all have regular checkout counters, and you are allowed to skip ahead in the waiting line until everybody in front of you has the same or fewer items. Do you think that would be a good idea? Well, I think it would be nice, because then I just go into the supermarket 50 times and always buy one item and always can go right to the front and don't have to wait anymore. But on the other hand, this would add a lot of overhead, because we would interrupt the current customer maybe that's already there and 5 items are already scanned, and then I'm going there and then, no, I only have 1 item, so it's my turn now, and then I can skip ahead, right? But it adds overhead. And if you have a full basket, you might have to wait forever, right, until the supermarket closes. But that's not my problem then. But of course, it's a problem for us operating system developers. If we introduce this algorithm somewhere in the system, then this becomes a problem for us, because our system might be very slow due to this. Let me check out this question on Menti. Why is first in, first out optimized for throughput and shortest job first for latency? They are not really optimized for this, but this is an inherent property when deciding to do that. And with the supermarket example, you can also see why. First in, first out. If every customer just queues up, and now it's the turn of the customer, and they scan all the items, and then they are done, and the next customer comes in, there's no overhead from switching between customers. But for shortest job first, I would optimize for latency inherently, because of the way the algorithm is designed. So the basic latency, if I want to compute, let's say, for 1 second, and the other one wants to compute for 10 seconds, then if I would compute after the other one, my latency would be 11 seconds, right? For the other one, it would be 10 seconds. So the overall latency that threads have waited until results are there is 21 seconds. In the other example, in, first out, if I was there first, this was first in, first out. So it would be 21 seconds. So it's not optimized for latency. In the other example, for shortest job first, we would turn this around, of course, because 1 second is less than 10 seconds. So the 1 second job would be scheduled first. So we interrupt the 10-second thread, the 10-second task. So this adds maybe a few milliseconds of overhead for the context switch, but then I have 1 second, I compute this, and after 1 second plus a bit for context switching, I have my recite for this first task. And the other one, how long did this one have to wait? Well, 1 second more, so it's now, instead of 10 seconds of waiting, it's 11 seconds. So overall, the waiting time then was 12 seconds. So it's 21 versus 12 seconds. And then 12 seconds is clearly better in terms of latency, overall latency. Why is the throughput for shortest job first worse than for first in, first out? Because with every task that is shorter than an already scheduled task, you're interrupting this, or this running task, you're interrupting this running task, and this adds overhead for the context switch. So you're adding overhead that usually would not be there. You're introducing this by adding these context switches. Will there be information about the cancelled exam today? Well, the exam is cancelled, so if you have any questions about that, you can ask them, of course. But in general, the information is that it's cancelled. And I provided some details in the email, and if you have additional questions, you can, of course, ask them. I also updated the website, so you can see the new point scales on the website. So let's talk about another algorithm. And we've already mentioned the name round robin. And I looked up where this name comes from, and I was unsure. Robin also is this, in German, Rotkehlchen, if I'm not mistaken. And they are also quite round, and round robin also has been used as an expression for that. But the round robin, as we use it today, probably comes from a different origin, namely from some form of signing a document at a round table, and basically signing in a circle, so that you don't know who was the initiator of some proposal that was maybe borderline legal or even illegal. And then if it was discovered, no one would be able to find out who was the head of this circle of illegal activity. And round robin basically works like this. You put all the tasks in a list, and then you always jump from one to the next. You divide the time into slices, and basically schedule the tasks only for a slice of time. That's a compromise between first in, first out and shortest job first. So yes, each task a fixed period of time, a time quantum. It's also called time quantum. If a task is not finished, then it goes back into the line, and then a different task can be scheduled in the meantime. But you can see that this, in some cases, will behave similar to shortest job first, and in other cases, it will behave more like first in, first out. But we can again brainstorm maybe a bit on the advantages and disadvantages. So round robin and the time quantum. What are your thoughts on this part? It's fair, yes. Many context switches, yes. It could have many context switches. Think about quantums that are very short or very long. Even absurdly short or absurdly long. Predictable, yeah, maybe. Depends again on what exact information we have, then it might be predictable, but the overhead, yeah, the overhead is probably quite predictable over time, yeah. Multi-threading with one core, yeah, sure, we can do that. Tasks don't get finished, but it depends on how long the tasks are. Not as exploitable as the others. Yeah. Think about maybe the example again with the supermarket. Imagine we would serve customers in a supermarket in a round robin fashion, or maybe we do serve customers in some real places in a round robin fashion. Think of restaurants, for instance. Easy to implement. Yeah, it's more complicated to implement probably than first in, first out, but danger with locks. The others can also, other scheduling algorithms can also have dangers with locks. Okay, let's see. Not responsive. Yes, it can be unresponsive. If you have many threads, then it's unresponsive. Long tasks may take forever, especially, yeah, if you have many long tasks, actually, this will have the same disadvantages as the shortest job first algorithm. Okay. Thank you. Let's see. What if I switch to a quantum that is very, very short? Let's say the quantum is 1 nanosecond. That will cause me a problem, right? Because then I will get basically no computation done. 1 nanosecond of computation, and then a few milliseconds of context switch. So this would be very, very bad because it has a lot of overhead. What if we take a quantum that is extremely long? Let's say a quantum that is 100 years. Then it would actually be first in, first out. Because then we are first computing the first task until it's finished, then the second task until it's finished, and so on. So depending on the quantum, we can optimize this algorithm into one or the other direction to resemble one or the other algorithm more. Let me show the Q&A for a second and go through some questions. Will we have to answer exam questions at the assignment interviews? Because if so, the new exam would be 1 week earlier than the original. Since that is so soon, I am not sure if I can manage that. I'm sure you will be able to manage that because, of course, we will not have a full exam there, but it will just be one exam question. Will the exam questions be part of the first or the second exercise interview? Both. We will have questions in both. Can we do an example on the website at the end of the lecture? Yes, we can do that. I did not fully get how to calculate the paging stuff. We can do that. I would not repeat the page replacement algorithms today because we will definitely not ask you about the page replacement algorithms in the first exercise interview. Can you tell us which videos or chapters are relevant for a one exam question? The first 3 to 4 lectures that were about virtual memory. They are relevant for A1, and then for the exercise interview of A2, I will announce that separately, but probably something from virtual memory 4 and 5, and maybe something on scheduling. At which Abgabegespräch will the exam questions be asked? In both. Will we need to do the paging calculations in the assignment reviews, and if yes, how? That is one exam question and very likely one that you will get. I would love to have this extra unit for the exam you mentioned in the mail. Yes, we can also do that, or we can just do that after this lecture. We have time and then we can go through that on the whiteboard. Will booting be relevant for A1? In terms of the exam question, no. We will not ask exam questions about the boot process. That's, yeah, that would not be nice. Okay, because the boot process is a lot, I mean, just looking up how it works and just following the specification from the CPU manufacturer and then running through a sequence of steps. There's not that much understanding in the boot process that you could learn there. And I'm more interested in exam questions that focus on understanding things and not so much learning a sequence of then write to this address, then write to this address, then write to this register, then write this value to this register. I wouldn't find that interesting. Let's talk about round robin. So the two different extremes that we have here would be a 1 millisecond time slice where all the short jobs are finished first, right? Because the first task, the long task, is interrupted, and then the long task continues. But this is very similar to shortest job first. If we take a longer time slice, then it's sort of like a mix between shortest job first and first in, first out, where first we compute a longer time, then these tasks finish, and then this task can continue. So basically, we could say round robin gives you the worst of both worlds. It's a compromise. But a compromise can be the best thing sometimes. Okay, there's another question in the YouTube chat. So only virtual memory questions will be asked on the first assignment interview. Yes, we will only ask questions from a... so I probably have to make this more precise. From the virtual memory lectures 1 to 4, the part on virtual memory that is relevant for the first assignment interview. You will get an exam question out of these. However, the teaching assistants can of course ask you anything from the lecture to check whether you understood the contents from this class that you needed for the first assignment. For instance, if one of the tasks was working with processes and threads. So the tutors might also ask questions about processes and threads. And if you then don't know anything about the differences between processes and threads, then this will of course be devastating and probably lead to a negative grade, because how can you participate in the first assignment if you don't know how these things work? So the exercise interview can contain questions about how things work, so what you would maybe describe as theory questions, but only if they directly connect to the practicals. Okay. Let's again take a look at another example here, maybe an example with long tasks. Now we have 5 long tasks, and you can see with round robin with 1 millisecond time slice, they would all be split up, and actually they would all see a higher latency. If you would use first in, first out, or shortest job first, this would actually perform better, because one of them would have only its own latency. Right? Let's say this length, this quantum is 1 millisecond, and this is, let's say in this example, it would be 5, right? So this is 5 milliseconds. So the latency here is 5 milliseconds, 10 milliseconds, 15, 20, 25. So the overall latency would be the sum of that divided by 2. The sum of that, and the average then would be divided by 5. So the average latency, but in this example, the average latency would be much higher, because the first one observes almost 5 times as much, and on average they would observe around 5 times as much as they would have themselves latency. So this has a much higher overall latency. So here in this example, round robin would be a disadvantage. Also, maybe you have I/O bound tasks and CPU bound tasks. And in that situation, round robin can be nice. So maybe some I/O bound task is scheduled, it requests something from some device, and then some CPU bound task can be scheduled, and then another CPU bound task can be scheduled. And then this one gets a response maybe, or issues a new request. Maybe it got a response already earlier, but it issues a new request, and then it waits again. And in the meantime, someone will be able to use the computation time in a meaningful way. There's a question, so we can actually not have a second chance with this oral exam. You have the practicals, and you have an exercise interview, and if you are negative, in some situations we will say yes, this is eligible for a second chance. In other cases we will say it's not eligible for a second chance. If it was not a serious attempt, then it was not, then it also wouldn't give a grade, and then we cannot give you a second chance in that situation. But if it's a serious attempt, then you will also have the opportunity to get a second chance. Usually we don't have any trouble with that. So if the tutor looks at the code that you contributed and believes that this is likely not enough to get you through assignment 2, and also for assignment 1 it was not enough, then maybe it's the better option to try it again another time. As I said in the beginning, we only have disadvantages if you repeat the class next semester or next year. That's only disadvantages for us. For you, it means you can have an advantage of saving some time if it's already clear that it won't be a positive grade in the end. So this is the only part that we are interested in there, informing you about the likelihood of getting a positive grade here in the exercise interview. There's another question. My question was related to the exam questions. Yes, the exam question alone will not get you a negative grade here, but in combination with how well you participated in the practicals, it can lead to an overall negative grade, of course. But the exam question alone doesn't contribute enough to the overall rating. Let's talk about the next algorithm, multi-level feedback queue, or MFQ, multi-level feedback queue. We have several goals here that we want to solve, that we had with problems that we had with previous algorithms. Latency, minimization. We want to minimize the overhead. We want to also make the latency predictable to some extent. We want to avoid starvation for long tasks as well as for short tasks. And then maybe some tasks are higher priority, some tasks might be lower priority. And maybe you also want to make sure that fairness among tasks with equal priority is maintained. And MFQ is not perfect at any of them, but it gives you a good compromise for these. And it's used in Linux, maybe also in Windows, maybe also in Mac OS. It's an algorithm that works quite well. MFQ, how can we imagine that? MFQ has multiple queues and they are ordered by priority. And each of these queues is a round-robin queue. So this is basically taking the round-robin algorithm, and each of these queues has its priority, and the processor will schedule tasks from these queues. The high priority queues have a short time slice, so they will be interrupted after a shorter time. The low priority queues have a longer time slice, so that the tasks can compute a bit longer. And the scheduler picks the first thread in the highest priority queue to schedule it. Then in the highest priority, the task starts, and if the time slice expires and the task has not finished, then the task is dropped one level to the next queue. So you would have something like this, maybe priorities 1 to 4, and the time slice is 10 to 80 milliseconds in this example, and you get some new task or an IO bound task, they would be here. And then as the time slice expires, they are moved here, and slower tasks, longer tasks would be down here. That's basically MFQ, and it has a lot of advantages over the previous examples. And I will just quickly summarize what we learned so far about single core scheduling. First in, first out was simple and it had a high throughput, but variable size tasks were bad for latency. Shortest job first is often impossible because we cannot predict the latency, and it also has some latency variance for long tasks. Also, significant overheads, right? The throughput is much lower than for first in, first out. Round robin, we have variable size tasks maybe, then it gets down to shortest job first. If we have equal size tasks, then it's bad. It's actually worse than FIFO or shortest job first. And yeah, if we have CPU and IO tasks mixed, then shortest job first actually performs better than round robin, because shortest job first will just take these IO tasks first and resolve them, and then continue with the CPU bound ones. MFQ balances latency, overhead, and fairness, and that yeah, is a good compromise and gets us closer to a fair and balanced situation than round robin does already. Okay, but this was just single core, right? And we started out with this slide about multiple cores, right? We might have multiple cores. So what do we need to change if we want to use MFQ on a multi-core CPU? We run into a big problem here because we said we have these multiple queues, and if we have these multiple queues and multiple cores that could access this queue is a resource and we need to protect it with a lock. So we lock the global MFQ lists, and then it's bad for performance. If every core needs to acquire this lock and check all the time, they might almost deadlock each other out of this list. But we will talk about deadlocks later on. Also, it can lead to cache slowdowns. If one core modifies the MFQ list, then this would be a dirty cache line in this core's level 1 cache, and another core that wants to read this has to request it from this other cache. So this can be very, very slow. Also, if you just take the first thread from the list, just because your core is not busy right now, and then it says, okay, give me the first thread from the MFQ list with the highest priority that has a thread that wants to be scheduled, then this could be very bad because the data from this thread could still be in a cache from another core, but not in my cache, but in the cache of another core. So it should be scheduled better again on this other core. So this can be really bad. And then we introduce a new concept to address these problems. That's core affinity. Each core in this example would then have its own thread list, and that's basically the affinity. In which core's thread list am I, or in which threads in which core's thread list, this way around, can this thread be? So it's an assignment from thread to core. And then you can protect this by a per core lock. So not every core needs to acquire the same lock, but every core just locks its own list because they each have their own thread list. In terms of SWEP, you could say that each core gets its own scheduler. Idle cores, so cores that have not enough work, can then say, okay, here, other scheduler, please give me one more thread. And they can steal a thread away from this other core, from this other scheduler. So that means we have multiple processors or cores, and they have their own such list of queues. Now we run into more problems, because if we do this very naively, then we might have a situation like this. So we have process 1 and thread 4 here. So it's always process and thread. And process 1 thread 4, process 1 thread 2, and here's process 1 thread 3. What if these threads, so we always say just schedule threads, don't schedule processes. But what if these threads actually need to interact with each other? This can be bad, right? Maybe they need to interact with each other to give to release a lock that this one will need. That can be really bad. So what can we do? There's this concept called bulk synchronous parallelism. And this, the idea here is that you have some synchronization barriers from time to time where all the processors just stop and then the workload is distributed again and then they continue with local computation. And only in this time in between they would communicate with each other. So that means that on each core you loop, compute on local data in parallel, then you have the barrier, then you send or select data to be sent to other cores, and that again can happen then in parallel. Then a barrier again, And examples for that would be different algorithms such as MapReduce, or if you have some fluid dynamics computation, or most parallel algorithms can actually be modeled in a way that they can be simulated with such a design. But this would reduce performance actually. If you've seen this on the previous slide, I will also show that again to you. We have this barrier here. What if this processor doesn't have to do anything until this barrier comes? What if this processor continues until this barrier and this one has to wait? So this can be bad. But of course, this is a design pattern basically that we see commonly, where you compute on local data and then you have some barrier and then you exchange data and then you have a barrier again and continue then with local data in the next loop round. Are there any methods of task length estimation? This is probably, if you're interested in this, then I think the lecture Real-Time Operating Systems might be quite interesting for you, because there the main problem is that you want to make tasks predictable. So you want to work with tasks that are, where you can, or with methods that make it predictable how long a task will take. And this is not easy or even solvable in the most general case. In the most general case, you cannot know how long a task will take. So only in constrained situations you will be able to compute or estimate the task length. But there are many, many influence factors that make this very complicated. Complex hardware today, where tons of different timing influences decide whether a memory access takes 4 cycles or 400 cycles. So it's very difficult to make these estimations on actual hardware. The producer-consumer delay, maybe. If you preempt one thread, then you have to either wait or stall the other threads. So we wait until everyone is done, and that can be really, really a long time. And if one thread needs something from some other processor, then this can be a long time and slows down all the other processors. So this is maybe not an ideal design, or it has at least this drawback. Other issues, preempting a thread on a critical path will slow down the end result. This is also a problem, right? We are computing something and we are preempting a thread here and then schedule a different thread. Then no thread in this critical path can continue because this one didn't provide its result. Or preempting a thread that currently holds a lock. Very bad. You might have observed that in SWEP that this sometimes happens. You're running some threads and they have, for instance, the loader lock or something like that, the arch memory lock, and they are currently destroying the process, for instance, and then they are preempted. There is a timer interrupt, different thread gets scheduled, and no one can access anything now because this one has the lock. Or even worse, the kernel memory manager lock, right? No one can use new or delete anymore until this lock is released. A solution that tries to address that and that has become more relevant recently is gang scheduling, where you schedule the processes to the threads of one process together. So they are basically walking on there to the processors like a gang. Okay. The application, basically, that's not what you define, but what the application does. It splits the work into threads, right? We can use pthread create to create an arbitrary number of threads. And that basically allows us to have multi-threading. But of course, the programmer might now assume that some of these threads run in parallel, and we can, as scheduler developers, we can take that into account and schedule, for instance, thread 1 of process 1 and thread 2 of process 1 and thread 3 of process 1 at the same time. And that would be super convenient because now they actually run in parallel. Very nice. They always run together if possible. If it's not possible, then you have different options depending on what you want to achieve. Because in the past, this was done for performance optimizations maybe, or to increase the efficiency of scheduling algorithms, but today it's also relevant for security. So if it's for security, then you would just not schedule anything on this other core. If it's for performance, you might schedule some other workload that doesn't need multiple threads. Linux, Windows, and Mac OS have mechanisms to dedicate a set of cores to an application, to pin an application to a set of cores. And on servers, this can also be very useful if you schedule the threads from one process or one virtual machine at the same time. Applications can pin threads to cores, and also the system might reserve a subset of cores for other applications, for instance in the cloud, where the cloud provider might want to reserve some cores for its own. Yeah, today it's also relevant for security, because scheduling multiple threads at the same time means that they can maybe spy on each other, and then you might not want to have that in a system where threads from different customers in the cloud are scheduled at the same time. Gang scheduling can make things more efficient, but also there still is some diminishing return. If you have more cores available at some point, still the efficiency will fall down. Another option that we have for scheduling is space sharing. So we can, instead of scheduling the threads dynamically, what we did before, the time sharing or time slicing, where we took the time axis for one core and basically sliced it and scheduled one thread after another, for instance with round robin, but also with MFQ, for instance. Another option is space sharing, and basically this assignment to cores goes in this direction of space sharing. In the cloud, this becomes more relevant because you sell a core to a customer maybe, and then this core is statically assigned to that customer, to that virtual machine. That of course minimizes the context switches, because you don't have to take this core out of this virtual machine very often. So it would be, for instance, like this. You have process 1 running on these 2 or 3 cores, and process 2 runs on these 3 cores. That would be space sharing. And with that, we are at the end of scheduling, and I will let me just see whether I can. Oh no, that doesn't work. Maybe I can hide the slide for a second so that we can check out some questions on Menti. Okay, I think it's this one. Yes. Let's see, there are some questions on Menti. What happens if we are not able to answer the exam questions? You will get a point deduction. And what if we fail to answer the one question? You will get a point deduction. And if you really are completely unable to answer it, it will be a significant point deduction. It will be difficult to get a positive grade then, but not impossible. Regarding the exam question, how will it be graded? It will make, so it depends a bit, as this is an oral exam. Of course, what you explain is taken into account, and if you are able to explain how it works, and if you are able to make the computation, and if you have a small computation error in there, then there will be no point deduction. If you cannot explain what you do, then of course you don't get any points for that. The exercise interview is intended to determine how well you have reached this learning goal. And in the most extreme case, the point deduction at the exercise interview that the tutor can give you is minus 100%. If the tutor thinks that your contribution to this exercise and to this course in general was that low. But in most cases, it will not be minus 100%. We rarely have those cases. And of course, the exam question is one aspect to that, to judge how well you contributed to your participation in the course, to your submission, and yeah, how well you achieved the learning goal. But of course, it's just the exam question is just one aspect of that. Okay, let me continue with the next part. We still have about 1 hour left, and I think that's perfect because I also have about half of the slides left, and they are about deadlocks. So we will talk about deadlocks now, and I will start with a very simple example that you already know. Classic deadlock example, wait, resource 1, resource 2, and then use the resource. And here we have wait, resource 2, resource 1, use resource. I think you all immediately see why this is a deadlock. If you don't, please ask your team members to explain you why this is a deadlock. This is something that you should see immediately. Should immediately recognize as a deadlock. The formal definition: a set of processes is deadlocked if each process in the set is waiting for an event that only another process in the set can cause. Okay, assumptions. Processes and threads, yeah, both could be deadlocked. Number of threads or the types of resources is probably relevant, but yeah, deadlocks can occur. Conditions for deadlocks. Well, we have 4 conditions here. The first is the mutual exclusion condition. Each resource is either currently assigned to exactly one process or is available. So a resource is either, we could also say it's locked or it's not locked. These are conditions for deadlocks. That means if one of these conditions is not met, then it cannot be a deadlock. So, for instance, if I don't have a mutual exclusion condition, if the resource is not locked at all, for instance, then I also don't get a deadlock. The hold and wait condition. Processes currently holding resources that were granted earlier can request new resources. So it is possible to acquire more than one lock, basically. Let's go for the next condition. No preemption condition. Resources previously granted cannot be forcibly taken away from a process. So we cannot force another process or thread to release its mutex, right? The process or thread decides that on their own. They must be explicitly released by the process holding them. And then the last condition, circular wait condition. There must be a circular list of 2 or more processes, each of which is waiting for a resource held by the next member of the chain. And this is something where you might think of pthread join as well, because there we also had a deadlock and deadlock detection, and we detected exactly this circular list. But we will get back to that in a second. All 4 conditions must be present for a deadlock to occur. Mutual exclusion condition, hold and wait condition, no preemption condition, and circular wait condition. And now, now as I list them here, it would not be interesting to list them again in an exam, but if you could explain why each of them is required, that would be interesting for an exam, I think. Okay, and why they are required, we will go through that now. Strategies to deal with deadlocks. Well, first, maybe that's a strategy that you also pursued in the beginning of SLP. Ignore it. maybe it also ignores us. Maybe it won't. I don't know. Yeah. Or you can detect and recover. You can avoid deadlocks altogether, or you can prevent deadlocks in the first place. So let's start with the first approach, ignoring. Yeah, so basically we must prevent deadlocks would be the requirement, but we maybe have a different approach, right? The mathematicians say we have to prevent them. They have designed these algorithms to prevent deadlocks. Maybe we have come up with something better because we are the software engineers, and we can first ask questions like, how often does the problem occur? how expensive is it to solve, right? How much overhead do we get if we use such a complex algorithm to resolve these deadlocks? So maybe let's not do that, but instead check how expensive this really is. So ignoring is apparently used in commercial products. Windows, for instance, it's used in Unix, in Linux. Problem is basically ignored. They don't use a methodological approach to that to avoid deadlocks. But it happens only once in a while that someone discovers a situation where the kernel deadlocks. So the probability of discovering such a situation is low. The cost to prevent deadlocks in the first place is too high, and the prevention might not be possible at all because we have very complex situations with hundreds of source files involved, and maybe it's not even possible. Maybe there's a deadlock situation in the design of the operating system in this part. And it's very easy to introduce such situations by design. Even detection is too expensive, so we don't do that either. We wait until someone runs into this bug and then we can resolve it. So maybe just use more comfort and less correctness. Let's go through one example. The resources in an operating system are limited. You might have a limited number of processes or open files at any time. Maybe you have a limit for that. Maybe it's limited by the memory that you have. And now you assume that all active processes, we are already close to the limit, that all active processes do another fork or open one more file, although we are close to the limit already. What happens? We are in a deadlock because every process needs that to continue. How likely is that? Probably not that likely unless someone is trying to attack our system in a denial of service attack. Detection and recovery. That's the next strategy. Maybe we don't prevent deadlocks, but we can try to detect them and deal with them when they happen. How can we do that? Well, we can draw these resource graphs and circles and detect them. Similar as we did in the case of pthread join, right? There we also kept track of the circle and tried to detect when a pthread join would create a circle. So we would detect when a deadlock occurs. So let's take a look at this example here. Process A holds R, and so this holds a mutex protecting resource R, right? Or we could also say mutex R to simplify it a bit. Process A holds R and wants S. B holds nothing but wants T. C holds nothing but wants S. D holds U but wants S and T. E holds T but wants V. F holds W but wants S. G holds V but wants U. Is this system deadlocked? That's basically a yes or no question, but it's not trivial to answer it without drawing the graph. So let's do that. If we draw exactly this down, then we get to this graph and we can directly see that there is a circle here. D wants let's check again. Process D wants to lock T, but it cannot lock T because B currently B wants to have it as well, right? Or D holds it. Let's check again. D holds U. D holds U in this direction. Okay, so it's drawn in the other direction. D holds U, so D would have to release U. Okay, but wants S and T. Okay, so D wants S and T. So this one is trying to acquire T, but T is held by E. E wants to have V, but it's held by G, and G wants U, which is held by D. And that, of course, is a circle, and there we are with our problem, with the locking problem here, deadlock. Detection, the next strategy, is easy visually, right? We can do that. We can create this graph, and there's an algorithm to do that, and basically there are many algorithms to detect circles in directed graphs. We can, for instance, use a depth first search, for instance, that we have done in pthread join as well. We take each node as the root of a tree, or basically as we extend the tree, we can check this only for our own node every time we extend it. Then we do a depth first search. If we ever come back to a node we have already been to, then we have found a cycle. When we have visited all arcs from a node, backtrack one level up. Or if you can search the other direction, then you might even save some time. And then if you are back at the start, you can say, okay, I didn't find a deadlock. But you need to try this for all nodes as roots. And we do that in pthread join, for instance, by doing this search whenever we add a new element, and then we are trying this for this node. So we are trying it for all nodes that are in the graph. It's not quite optimal because we have to search for some time, and yeah, it's wasted computation time. Sure, but if we can avoid a deadlock, maybe it's worth it. That's a design decision. When do we check for a deadlock? On each request, earliest detection, but also expensive, like with pthread join. Maybe sometime in a while, but then how do we resolve it, right? Do we then later on tell pthread join, oh no, it was not successful, you created a deadlock? And which pthread join gets this response then? Or when we have nothing else to do, maybe as the idle thread has nothing to do, we can check for deadlocks. And then, yeah, what do we do? Preemption, rollback, kill processes. That's not easy. And this is the next step. So detection and then recovery or preemption. How can we recover from that situation? So we would have to take away resources from a process. This process would not be allowed to lock this anymore. Or in the case of pthread join, to perform this join operation. And this might be possible with some resources, but in other cases, it's not possible, right? It could have side effects. Imagine I have locked the disk and now someone takes the disk lock away from me because I should not have run this, but I already sent my request to the disk. That's not working, right? So it's difficult to impossible, somewhere in between those, to implement it in a generic way. And manual intervention might be required here from case to case, depending on what exactly is locked. And this is not a strategy that we can implement in a generic way. Another option is using rollback mechanisms that you might know from databases, where you also have this begin instruction and the commit instruction or the rollback instruction if something went wrong. And you could implement something similar also in any other computer system where you constantly set checkpoints. So you store all the data that you, the current state that you currently have, the memory registers, back up everything. And then when a deadlock occurs, you select a process and set it back to the checkpoint before the resource was deadlocked, before the lock was assigned to this process. Does that sound realistic? Maybe not. Maybe this is also way too expensive to do. Or maybe a much simpler solution, right? Once we're at solutions that no one wants, maybe just kill the process. Simple and effective, totally fine. Just kill the process. Oh, this one was part of a deadlock. Let's kill it. Also not really a satisfying solution here. What if this resolves the deadlock? Sure, then you resolve the deadlock. But what if it doesn't resolve the deadlock? Then you just kill more processes and continue and continue. Which one to kill? Yes, probably one you can restart. But again, this is not a generic strategy. It's not a great idea. And some processes might have side effects. For instance, interacting with the disk, interacting with the database, writing data somewhere, changing data. You can't just kill this process. It might be in the middle of changing something. So maybe also not a good strategy here. Maybe it's better to avoid deadlocks. Processes that ask for resources one at a time. Avoidance would check if the resource can be assigned safely and assign the resource only when it's safe. And this is basically how we applied this previous detection mechanism now in a secure and safe way. And this is what we've done in pthread join again. We use this detection mechanism to implement deadlock avoidance. Is there an algorithm that can do that? Yes. Basically, you can use, in some situations, you can use detection algorithms. In other situations, it depends on what information is available in advance. For instance, for pthread join, you have all the information you need to decide whether or not it will deadlock. Yeah, avoidance is rarely practical. There are only a few use cases where you can implement it. So prevention might be something that is a better option. Preventing deadlocks altogether. Recovery is difficult. What can we do? We prevent them by excluding one of the requirements. So which requirement can we exclude? Maybe we can get rid of one. No mutex, no deadlock. Does that sound like a good idea? Yeah. Sure. What happens? Yeah, mutual exclusion is a requirement. This is practically impossible. You have to use mutexes, otherwise everything breaks, right? Avoiding locking. Of course, avoiding locking is bad. But in some cases, you might actually use this strategy to avoid or to optimize the locking situation altogether, the synchronization situation altogether. For instance, let's assume a thread for no reason really, just because it maybe was more convenient, accesses the global list of copy on write flags, the global array where you store the copy on write counters. And it wouldn't have to access this array. You have to lock it, and of course that's inconvenient. Maybe you can avoid using this resource. Maybe you can get the same information from somewhere else, and then you don't have to apply this lock, and then you can also avoid locking problems related to this. Sure. Or try to make sure that as few processes as possible could possibly access a resource. This is another strategy that you will use in assignment 2, where you have, for instance, the swap disk, and you don't want every thread to be able to access the swap disk, but instead they will all interact with the thread that is responsible for interacting with the swap disk. And by that, you basically divide these two locking areas, and you cannot have a deadlock across these. Hold and wait. Prevent that processes that hold resources can wait for more resources. So basically, once you have a lock, don't allow acquiring more locks. This is again not easy. So this is again difficult in different situations, and strategies might be requiring all processes to request all locks before starting the execution. You will see that, for instance, for copy on write, when you want to set the page as writable, maybe you have to set it to writable in multiple processes because you deduplicated the page. Do you now acquire the locks for both processes after each other? In which order? Do you require them both at once? What if you can't get both locks? So this is something to consider here. Maybe you can avoid this situation altogether. That would be great, but maybe you can't. So this is something that you have to think about, whether you can avoid this condition. Processes don't necessarily know that what they will need. For instance, you might know this situation from the loader and the arch memory, where you want to map a page and you don't know whether you will need a new page for the page table. And getting a new page for the page table would require getting the page manager lock. So you don't even know whether you will need the page manager lock. And then locking the page manager every time that you want to map a page might also be inefficient. So this is, again, not a really nice solution. All of these solutions you will find all have drawbacks, and we only can pick which one has the fewest drawbacks for us. But we will usually not find very beautiful solutions here, just ones that are less ugly than others. Very defensive and very bad for effective resource utilization. An alternative, you can release all resources first when acquiring a new one. So releasing all locks whenever you want to acquire a new lock, and then try to get all of them again at once. Again, this can go down to a busy wait, basically, where you lock and then try again and try again and try again, and it doesn't work, and you just keep busy waiting. The next step, next condition, preemption condition. Maybe you can avoid that threads can be preempted. That's also rarely possible. Usually threads can always be preempted, and then other threads can be scheduled in the meantime and work on resources. The circular wait, maybe we can fix the circular wait situation. So we might introduce something that prevents that we ever get a circle. And there's a very easy idea. There cannot be a circle if you only allow one resource to be held, right? No, more seriously, you could number mutexes. You could provide global numbering for all resources. And processes can acquire as many locks as they like, but only in numerical order. Or resources, locks. I'm always interchanging here resources and locks, because of course we are talking about acquiring the resource. That means acquiring the lock for this resource. So we can request the resource. That means acquire the lock for this resource, but only in numerical order. But how do we get this numerical order? I mean, it's great. No cycle can exist because we cannot acquire lock. Let's say if we order it this way, we can acquire lock 2, and then we can still acquire lock 3, but we couldn't acquire lock 1 then. We would have to acquire lock 1 first. So it's sort of like a hierarchy. It's really nice. And this is a strategy that you will definitely use in the practicals. All students use this strategy in the practicals. It's a very practical strategy, even though it's difficult for the generic case. But you design the software, you can come up with this numbering scheme. Yeah, it can be difficult to find a working numbering scheme. What if resources are dynamically allocated, right? Then this order might change, there might be new elements in between. Does that become a problem? It might become a problem, but in some situations maybe you can also work with that. Yeah, then another solution that you might come across, especially when working on copy on write or swapping with copy on write, the two-phase locking approach. Avoidance and prevention is maybe not working in all cases. I think prevention is actually quite good. I think that's a cheap strategy that you can always pursue as long as it works. And if it doesn't work, then you can fall back to two-phase locking. For specific applications, you can use algorithms that are really good. For instance, for database systems, there you frequently have the situation that you need locks on several records. And then you can just lock all of these records and then update them all. If you have multiple processes, that's the real danger of a deadlock, because in which order do you lock the records? If you first take your record and then the one of the other, then the other might do the same, and it might be a lock inversion again, a classical deadlock. So with two-phase locking, we are again going back to this try again loop. So we start in the phase one, we try to get all locks for all records, and if it's successful, then we update all the records and release the locks. If we're not successful, we go back to phase one, and we're again in this busy wait. Of course, this can be bad, but sometimes we don't get around this. And with that, we are almost at the end. One topic again is relevant here, same as for scheduling, same as for swapping. We also again have this topic of starvation here. So what type of starvation do we have here? Well, starvation is closely related to deadlocks. And the problem is that you will have some policy to decide which thread gets which resource. And this can lead to a situation where some process never gets the resource, even though they are not deadlocked. But you can usually handle that and this type of locking problem by implementing, for instance, if you're working with semaphores, you might implement semaphores in the SWAP kernel or in the SWAP user space, the locks. You might implement a policy there that can avoid this altogether, and for instance, a first come first serve basis where the first thread that tries to allocate this lock will also get this lock as soon as it's free. With that, we are at the end of this lecture, and I will take time to go through another example with you, but I will also just show the Q&A here. So two-phase locking is needed for copy and write to lock the page reference table where the amount of reference is stored. You can implement that without two-phase locking. You can just introduce a hierarchy there and try to disentangle some of the resources that you would need there. Maybe you can in advance already figure out how many pages you will need. So in these situations, it will be possible to work around. But in some cases, two-phase locking might be necessary. So every year we see many student groups that have to fall back on two-phase locking because their design doesn't allow a more beautiful implementation. But two-phase locking, you have to be very careful there because this can very easily degrade into busy waiting, and busy waiting is something that we want to avoid. Okay, so for some reason I don't see the question here on my phone, so I also can't click it away. Let's see, maybe if I refresh. Yes, okay, this works. And with that, we are at the end of the questions, and we will now take some time to go through another example from the exam questions page. Let me just put a chair here. Okay. This is bad. Now I'm too small here. And maybe. Yeah. Okay. This works. Let me maybe adjust this a bit. So now you are able to see me also, and we can start with an example. Let me just open the test system page for that. So I will open that, and yeah. Okay, that's basically the test system page, and we can maybe scale this to a nice size, something like this maybe. Okay. And now we go for this example test page, and I will copy the link here. Okay, perfect. And we can also post this in the chat. So here you can click on this link, and then you will also be able to solve this together with me. Okay, this is a longer example with multiple levels. So let's see how this works. So we are again back to page translation, and we are talking about address spaces, virtual address spaces, physical address spaces, 23-bit virtual address space, and a 15-bit physical address space. Okay. I want to do something today to enable you to understand this in a more code-oriented way. So I will open this web source code now. And in this web source code, I will show you the window in a second. Okay. So that would be this one. This is this web source code, and I will copy in this example from the test system. So what we had here was basically this sentence: 23-bit virtual address, 15-bit physical address space. And I'm now interested in the page table entry. There are lots of page table entries here, and I will just kick out all the stuff that I don't need right now. So I don't need the page dear page entry, because that's for 2 MB pages. Page dear page table entry, that's fine. Page dear pointer table page entry. I don't need the page entry. Page dear page table entry, page table entry, page dear pointer table page dear entry, yes. And then we have here the page map level 4 entry. And now we will copy in exactly what we had on the website. So what we had on the website was basically this frame, right? We had, I don't know how many bits, I don't know how many bits, and I don't know how many bits. We will figure this out. But we had valid. Okay, this was valid. Okay, let's align this again. So just that you see that this is really exactly executable, really exactly what we are working with in SWAP all the time. Writable, readable. Okay, readable. And about these others, we still have to figure out how large they are, but we know that there's only ignored, frame number, and ignored. So basically we can just say it's this ignored and this ignored. Okay. Page ppn, we have to figure out how large they are. This is basically our first task. How large are they? And for that, we will go back to the test system. Okay. So in the test system, we can now try to figure out how large this is. A page size is 64 bytes. 64 bytes, we want to fill this page with page table entries. So we would have to figure out how many page table entries, and this would be one page table entry. This is the struct that I just wrote in the code. How many of these page table entries are fitting in 64 bytes? Okay. For that, we need to know how large a page table entry is. And we start here by looking at the page size. The page size is 64 bytes. 64 bytes, that's 2 to the 6, right? In German, 2 hoch 6. 2 to the 6. That means we need 6 bits to be able to address every byte within these 64 bytes, to represent any index pointing to any location in these 64 bytes. 64 bytes. 6 bits, and we only have, because the page offset is always at the end of the address. We know that, we learned that. That means that we have 1, 2, 3, 4 bits already. 2 bits must be missing to get to this page size. Okay. The next step is the page size also has some interaction with the physical address. the physical address space is 2 to the 15, 2 hoch 15, 2 to the 15, and the page size is 64, so it's 2 to the 6. That means 6 bits are already used for the page offset, and if we have 15-bit physical addresses, we actually only have a subset of these 15 bits for the frame number, for the physical page number. And that's exactly 15 minus these 6 bits that we already used. So it would be 9 bits. 15 minus 6. And the 6 I got from these fields here. Okay. And the next step is we have to compute these ignored bits here. And we have 6 bits here, we have 2 bits here, 9 bits here. In total, this is 15 bits. Of course, this is in total 15 bits because we have 15-bit physical address space. So this is also a good check. If you want to make sure that you've done everything right so far, just check whether these fields together are 15 bits, are exactly the physical address space size. Okay, so far everything all right. How large should this entry be? It should be a multiple of bytes. It should be actually a power of 2 number of bytes. So it should be something like 1 byte, 2 bytes, 4 bytes, 8 bytes. Anything else is super ugly to handle, right? Working with 5 bytes, fitting 5 bytes into 64 byte pages, that's not nice. Working with powers of 2 is nice. And next power of 2 in this case, think about it, 2 to the 15, 2 to the 15. We have to do something else. We have to divide it by 8, right? To get to bytes, from bits to bytes. This is 15 divided by 2 is not nice. 16, 1 bit more, would be nice. 16 divided by 2 would be 8. Divided by 8 would be 2, this way around. Divided by 8, then we get from 16 bits is 2 bytes. So 1 bit is missing here. And that gets us back to our code. And in the code, we can directly also extend this. So this is the correct answer now, 2. And then we had 9 bits here, and we had 1 bit here. That's our page table entry. And now we can copy this because that's what the assignment page said. And that's also what you observe in the page table paging definitions in SWAP. The page tables on the different levels, they look very similar. Let's take a look again. Take a look at this. This is almost identical here. And up here as well. It's almost identical on each of these layers. And we have exactly the same in the assignment here. It says each page table entry on each layer has the following format. So that means that we can copy this now in our paging definitions. Okay, they all have the same format. Okay, copied this in here. Okay, very nice. And it almost fits on one page. Okay, so let's check again the assignment page. What else we have to change? So we can see that the R, so we have that here. The R, the W, and the X bits are only used in the last page table level and ignored on all higher page table levels. Let's do that. Well, we can save some bits here. We can just remove them, right? This is the highest level, maybe 3 bits more. So that means here are 5 ignored bits. We can also introduce, to make this a bit nicer for you to follow, we can also name them ignored 3. Okay, ignored 3, and this would get 3 bits, right? Because we now ignore these executable, writable, and readable bits. Okay, very nice. So now we have the entire paging hierarchy in code in our editor. Okay, looked fairly easy. So let's take a look at this example again. What is the next step? The next step, we know what the size of each page table entry is. It's 2 bytes. 2 bytes. How often do 2 bytes fit into 64 bytes? 32 times. That means on the last level entry on the, it says here, with this many entries on the lowest level. We start with the lowest level, and this lowest level will have 64 divided by 2 entries, right? Because one entry is 2 bytes, so we can fit 32 in there. There's only one thing we have to consider here. Is the virtual address large enough? And for 32 entries, that would be 2 to the 5 would be 32. So it's 5 bits. 5 bits plus 6 bits from the page is 11 bits. So it's smaller than the virtual address. So it's fine. So here's the full 32 entries. So we used 5 bits already now for this last entry. And I will draw this on the whiteboard maybe at the same time here. So the virtual address, how is this constructed? And it's constructed like this maybe. And we have the last part here was the 6 bits for the page. Then we had the next 5 bits. So this was the offset. Then we have the page table index, right? This is the 5 that we just computed here, the 32. We can also write that here. 2 to the, probably we write it just like this. 2 to the 5 equals 32. Just so that you know why we have 32 here, and there I wrote 5 in the address. On the next level, we can again put 32 because we still have enough bits left. We have 23 bits left, 23 minus 11 bits left, 5. So that's the page directory index. If you want to use the wording from Intel, and then we have space for another 5. So we continue with this scheme up to 23. So it's 11, now it's 21. So there are 2 more left. So it would be 2 bits here. So P, D, P, T, I, and page map level 4 index. Okay. That would be what the virtual address looks like. And let me check whether it is correct. 32. So we now have 5, 2 to the 5, 2 to the 5, 2 to the 5. And here it would be 2 to the 2. It would be 4. And that means we have 4 levels in total. If you have any questions, you can always ask them in the chat or in the Menti, and I will answer them then. Okay, we solved this first part. This part is fairly easy. This is the easy part of the assignment, and I think everyone will be able to run through this part in the exercise interview. It won't be any problem. So the next part is we do this address translation. So that means that we take this address and we read the memory from there. And what do we do then? And for that I will go back to the code. We cast this memory location to this struct. We interpret whatever is there at this memory location as this struct here. And we don't need the code for that. We can just do that on the paper, right? So we will go to this address 1B00. Oh, that's actually, we have to take a bit more care there. So let me maybe make some room for that. So I will reduce the window size just a bit so that I have some more space on the whiteboard. I can probably also move this one a bit more up here. Yeah, that works. Okay, some more space on the whiteboard because we have to think about all these indices here. And the first address that we want to look up, we have to take that into account. The first address that we want to look up, oh, that's a long address. Wow. Okay. Let me just reduce the window size a bit more so that I can see everything. Because otherwise I don't see everything. Okay. So what do we have here? We have the address is null x 7 to 66AE. Oh, that's a long address. It will keep us busy for some time, but that's fine. And to stay in terms in Intel terminology, CR3, the value of CR3 equals, and we can just write that down from up there, null x1b00. Okay. And that's the address that we want to look up. It's basically just, we cast this to an integer and dereference it, something like that. So we dereference this location. So what do we have to do first? We have to determine what are all these fields here. Offset, PTI, PDI, PD, PTI, PML4 index. So let's do that. We start with the offset. That's the last 6 bits. So it would be the lowest 6 bits of this. So that means we have to think about A. A is 1, 0, 1, 0. The topmost bits are gone, so it is just 1, 0. And we know that 1, 0 is 2, right? Okay. And that means that the offset, we can also write it like this. Null x AE. And then the offset would be null x2f. If you find that easier, then you can say, okay, now I will check, okay, the E stays the same, and from the A only the lowest, the 3f, sorry, 3f. That's 2 to the 6. And from this one, only the lowest 2 bits survive. Okay. And then, of course, this would then yield null x2e. The next step, we have to compute the PTI. The PTI is shifted to the right by 6. So it's PTI, and it's 5 bits. So we have to take the lowest 11 bits. Let's take the lowest 12 bits for now. And I know that the topmost bit of the 6 is not set. So it's totally fine to just say 6AE. I will also remove this null x because it's just confusing if we always see the null x here everywhere. It's hexadecimal, hex numbers everywhere. And this has to be shifted to the right by 6. That's the same as removing the last character and shifting it to the right by 2. That's, well, the same as shifting it to the right by 1 2 times. Okay, this one is easy because this one, A, is, we know that A hexadecimal is 10. And 10 divided by 2, which is the shift by 1, becomes a 5. 6 divided by 2 becomes a 3. Okay, this one done. And the next step, okay, now we have to shift this another time to the right by 1. So the 4, here's a 1 and a 4 in this hex character, right? And the 4 becomes a 2. A 2. The 1 bit is gone. And from this one, from the 3, 1 bit goes over to this. So the topmost bit is set, which makes it an A, and 1 bit is still left, so it's 1A. Okay. Let's go on. Page directory index. And the page directory index would be shift this to the right by 11. Yeah, okay. And we need the lowest 16 bits. 16 is very nice because that's exactly 66AE. And that's shifted to the right by 11. That's the same as shifting it to the right by 11. Now I removed 4 bits. Removing another 4 bits. 3 bits remain because I already removed 8 bits. Okay, so we have to remove 3 more bits from this. And this is maybe, yeah, maybe is this easier or is it not easier? So then we get 3. The other option, what we can do here is And this is some trick that I like very much. I can also shift this to the left by 1 and then shift this one to the right by 4, which is much easier. So this one shifted to the left by 1 will become 6. Shifted to the left by 1 is C, and then shifted to the right by 4. So we have to keep this one shifted to the right by 4. That's trivial because that just means we remove the last hex character. It's C. Okay, let's see whether we are doing everything right so far. We have to take care that actually we are removing all the bits that we should remove, because this is just 5 bits here, and the largest index that we can represent with 5 bits would be 1F, right? 1F, 5 bits. So 1A is below that, C is also below that. Let's go for the next one, PDPTI. That's the 3rd level. And then we take 5 more bits, and that means that we have now 21 bits. Yes, 21 bits. So we have to now take all 20, so we have to take 24 bits basically. But we can, if we only need 1 bit from the topmost hex character, then it's actually easy. So it's 4, 8, 12, 16, 20, and 1 bit from this one, and it's a 1. So we can already solve this part. So it's 1, 2, 6, 6, A, E. And if there are any questions, you can always ask in the YouTube chat or in the Menti. I just done the first part of selecting the 21 bits from this pointer. This was my pointer. Pointer is this. You can't see this part on the whiteboard. Okay. And I have to shift this to the right by, okay, by 16. Oh, that's nice. Shifting to the right by 16 that's very easy. That would be 4, 8, 12, 16. Done. Okay, 12. And then we have the page map level 4 index. And that is exactly this number up here, 7266A, E, shifted to the right by 21. And that's the same as shifting it to the right by 20 and then by 1. And that's exactly what we will do. We shifted first by 4, 8, 12, 16, 20. So it's now to be shifted by 1. 7 shifted to the right by 1. That is very easy. That's 3. So 7 shifted to the right by 1 is 3. Very nice. Now we got all the indices, and let's see whether this is correct. So what we have to do now is, this is our index, and we basically want to access this array that starts at this address and at this index 3. But we have to take into account that the entry size is 2. So we have to shift this to the left by 1. So the first address to look up is null x1 b and 0, 0 plus 3 shifted to the left by 1. Because the entry size is not 1 byte, then we would have to shift it by 0, so not at all. If it's 2 bytes, shift it by 1. If it's 4 bytes, shift it by 2, and so on. You always have to shift it by the number of bits that are taken away by your entry size. So shifting this to the left by 1, or you can also multiply it by 2, which gets to the same result, by plus 6. So the first location to look up would be 1B06. Let's look this one up. 1B0, that's a very large address. I hope I didn't make any mistakes here. 1B06. But so far it looked quite okay what we did. B06, so it's 0, 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5, 6. This would be the first entry, and we get from this the page map level 4 entry, which is 92A1. And this 92A1 is now what we put, let me just show that again for a second, in this page map level 4 entry. So we have to just cast this hex number here into this struct. Okay, we can do that, sure. And we can do that without the code. That code is not necessary here. So we go up to the start. Okay, and we want to compute. First of all, before we do anything else, we want to check whether this translation can be valid. And so far, it can be valid because the lowest bit is set, so it can be valid. Okay, then there are a lot of ignored bits, and this is the next part that I would recommend. Setting all the bits that are not the frame number bits, setting them to 0. So that means we set the topmost bit to 0 in this 16-bit number. Okay, so in this case, the 9 becomes a 1 because we set the topmost bit to 0. Then we set the lowest 6 bits to 0. That means this one is 0, and the A becomes an 8. Okay, so it would be 1 to 80. That would be the physical address where the next level starts. Okay. We now need the physical page number, so we divide this by page size. Okay, let me just write that here. So it's 1280 shifted to the right by 6. We could also divide it by 64, but dividing it by 64 is much more complicated than shifting it to the right by 6, because keep in mind that this is not a decimal number. It's not a decimal number, so you can't just divide by 64. It will be wrong if you do that. So 12080 shifted to the right by 6. This will be the same as shifting this to the right by 2. And this is the same as shifting this to the right 2 times by 1. And this will be 4. This will be 1. And this will be 0, but it gets us a bit here, so it's 94, and this has to be shifted one more time, and then it will be the 8 here becomes a 4, but the 1 bit goes over there, so it's a 4, and this 4 becomes a 2, but it gets a bit from the top, so it's 4A. Let's check whether 4A is correct. Null x 4A. It's correct. Okay. We got the first one right. Great. Okay. Could you follow so far? We are basically just doing what the operating system in some cases does, or what the hardware does. So what the operating system does, whenever you call resolve address, the operating system does exactly that. And if you access a pointer, the hardware does exactly that. Okay, but it does more, right? We only went through the first level of the translation so far. So let's do the next step, 12. So we have 1 to 80, because now we have to continue with the physical address. So we would have to shift this 4A here. We would have to shift this to the left by 6. but we just shifted this one to the right by 6 and it got us 4A. So we know that already know that 1280 will be the next address to look up. So here we will look up 1280 plus, and we need this index here, 12 shifted to the left by 1. So this is trivial. 12 shifted to the left by 1 becomes 2, 4. Very nice. Okay. And 2, 4. I can solve that because 2 plus 8 becomes 10. That's an A. And plus 4, 0 plus 4 becomes 4. So the address to look up is 12A4. Let's go for it. Next, 12A4. So it's 0, 1, 2, 3, 4. This is the address that we have here, and it's, oh, this one was a lot faster now. Now that we know how to solve this, this one was working actually very fast. So the page directory pointer table entry is 86 and then 3F. Can it still be valid? Yes, because F has the lowest bit set. So it can be valid. We don't know yet whether it's valid or not, but it still can be valid because the valid bit is still set on this level. Next step, we remove all the ignored bits again. We want to get rid of these ignored bits. We don't like them. We set them to 0. That means that the 8 becomes a 0. That means that the 3F, F becomes a 0. And 3 also becomes a 0. So the PDPTE, that's not the PDPTE anymore. That's basically just derived from the PDPTE. That's the physical address that we look up next on the next level. The physical address of the page directory. And we want to compute the physical page number, so we have to shift it by 6 again. So this 600 shifted to the right by 6 is the same as 60 shifted to the right by 2, and that's the same as do we still have space? Yeah, 30, and that's the same as 18 shifted to the right. It should be shifted to the right by 1, and that's 18. So the page number here would be 18. Very nice. That's correct. Perfect. Okay, next one. Now that it's working so smoothly, we can just continue. So we have here 600. Again, we don't go back from this page number because we just had the physical address already there before. 600 plus 66 shifted to the left by 1. That's why I usually remove these steps from in the middle, because the 66 almost got me, and the correct index here is C, right? This one. This was just an intermediate step. So let's just maybe add something so that I don't pick this one up again. I usually remove this resize because I get easily confused. C shifted to the left by 1. Well, that should be C is 1100. So 1 will go over to the next hex character and 1 will stay there. So it's then 18. Okay. 18. Yeah, I could have immediately written 618 and 618. And we will check out what the page directory entry at this offset is. So we will do it like this. Page directory entry, check out x618. Okay, so we have to check out where this is. In this time, because 8 is pretty much in the middle, we could also count from the right side. It's F, E, D, C, B, A, and then we have 9, 8 here. 8. Let's just maybe check whether it's correct from the other side, but sometimes it's more convenient to count from the right side. 0, 1, 2, 3, 4, 5, 6, 7, 8. Yes, same result. So the result here is null C6D. Can it still be valid? Yes, because the lowest bit is set. It can still be valid. We still don't know whether it's valid, but it can still be valid. Okay, C6D, we again do the same trick. We set the lowest 6 bits to 0 and the top 1 bit to 0. And now we have C6. Very nice. C6. C6 shifted to the right by 2. That's the same as shifting 6, 3 to the right by 1. And that's the same as 3, 1. Okay. I somehow have more space on my whiteboard today because last time it was already cut off around here. Maybe the webcam is a bit different. So 31. Let's check whether 31 is correct. Null x31. Yes, it's correct. So now we know where the page table is, and we can continue with this address here. So we look up C60 plus 1A shifted to the left by 1 because of the page table entry size again, like in all cases before. 1A, if we shift this to the left, that's again, yeah, fairly easy. So the 1 becomes a 2, and the A, well, 1 bit from the A goes up to the next one, so it becomes a 3. And the other bit was a 2, it becomes a 4, so it's 34. Okay. Hex numbers are very nice because all of these computations, as you realize, only ever influence 1 bit to the left or the right. All the other operations are all in place, and I only have to compare 2 hex characters with each other. That's much more convenient than working with decimal numbers where everything falls through the entire number, at least if you work with computers. C60, 34, that might become then C94, and we will look up the page table entry here, and this is the first time where we will know whether the address is valid or not. Okay, let's see. C94. We have here 0, 1, 2, 3, 4, 14 ED. Okay, 14 ED, and there we know we can directly read the bits from here. Let's go back to the code. We are now at this level already, right? And we know that this is now interpreted in the following way. So this is the D. Then we have for the remaining part we have 14E, just to show that in the code again as well. And we know that D is 1101. So this decomposes into a 1 here, a 1 here, a 0 here, and a 1 here. This is exactly what we are working with in code. This is exactly what the hardware is working with. We're just doing this on the whiteboard so that we fully understand how things work, right? Okay, so, and this would also be split up into these bits, of course. It totally makes sense. And then we can just go up here, and also we can just enter this here, directly because now we know what the values are. It's readable, it's writable, it's not executable, and it's valid. Did I do something wrong? 14ED? In my opinion, it should be readable. Maybe I miscomputed something, or maybe I copied something wrong. So this is the point where we should probably check, but you can practice this very often and check and make sure that the mistakes that you come across don't occur too often. So we will check that now. What would be the page number in this situation? So in this situation, I would assume that the page number would be 14E, this would be 0, this would be a C, so we would get 14C0, and we have to shift this to the right by 2 and 4 more. So this is then 3, this 4 becomes 1, this 1 becomes an 8, and then a 4, so it's actually a 5, so it would be 53, and 53 is probably wrong. Yeah, I think I know where I made the mistake, and it must be that I looked up the wrong address on the previous layer. So where did I go wrong? Let's see. Okay. Let's maybe start at, let's start checking these results here again. We had here the 66, was this correct? So we had the lowest for the page directory index. We ignore the lowest 11 bits. Then we take 5 bits. I think that makes sense. And also we know that this address was correct. So we know that this one, we know that this one was correct. We know that this one was correct. This one was correct. This one was wrong. So the error must be in this line. So 1A is wrong. 1A must be wrong. Let's check this one again. And we take for the page table index, we take the lowest 11 bits. That's 6AE. That's correct, right? So far we had everything right, yes. So 6AE, and this is shifted to the right by 6. That is the same as shifting this to the right by 2 and omitting a hex character. Now let's shift this to the right by 1 and then again by 1. And it becomes, A becomes a 5 and 6 becomes a 3. And then we shift this another time to the right. And then we get, oh, I see what I did there. 35 shifted to the right by 1 was not 14 or whatever I had there. It's, no, it was 1A, right? Yes, it should be 1A. Because this is 1 bit from the 3 goes off to the next one. So it would be shifted to the right. Maybe I can also write down what I do here. So it's basically 1, 0 plus 8 plus 2. That's what I compute here. Because the 5 becomes a 2, the 3 becomes a 10 and an 8. And that would be 1A. So it should be 1A. I think that's just what we had there before. So where did I miscompute then? C60, C60. Okay. Let's see. Some part went wrong. 1A. C60. plus 1a shifted to the left by 1. And this should be 34. So this is also maybe a good point to point out. If you can explain what you did and why you did it, and for some reason the test system says you're wrong, that's maybe a good point for a bug report. So this will become a 3, and the A has a 2 set, so it becomes a 4. So it's 34. So it must be C9. 4. It must be C94. Maybe we didn't look up C94. Maybe I did the mistake there. So it's 0, 1, 2, 3, 4. I don't know why this one does not like this bit here, but I'm sure that it should be C94. Maybe there's a bug in the computation somewhere, but if you would explain it to me like that, I would give you all the points, and the tutors would do the same. So I cannot tell you right now why it doesn't accept this result. What we can do, of course, is we can try a different address or a different example. Maybe this example is buggy due to some combination of bits, but doesn't sound like it. D is 1 1 0 1, so it should be 1 1 0 1, and my impression is that this should be we had the number down here, 14ED, and this would be 14E. We have to shift it to the right by 2 more, so it's 4. So the 4 becomes 1. The 1 becomes a 4 in the next hex character, so it's 5. And the E becomes a 3. So it's 5 3. It should be 5 3. I don't know why it's wrong. Maybe you figure out what I did wrong, and if you do, please let me know. Otherwise, we can continue with the next example if you want, and see whether the same problem occurs there as well, or we can switch to a different address address example. Maybe that works better than. Let me just check. No, it doesn't like this. Okay, I will just move to another example, and I will also post this in the chat, and we can try this one. Okay. Okay, yeah, different example, but it pretty much works the same way. I will remove these because we don't need them for now. And I will try to solve this now a bit quicker because we've already seen the long path now, and maybe we can solve this a bit quicker now. So it's a 64-bit page size, so we have 2 bits ignored. We have 20 bits physical address, minus 6 bits is 14 bits. Then we have 16 plus 4 is 20, so we still have 12 bits left until we are at 32 bits to get to the next 4-byte size for a page table entry. That means in one entry is 4 bytes, one page is 64 bytes. That means we get 16 entries on the lowest level. We have only a 16-bit virtual address, so we have to be careful there. So this is 4 bits. We have 6 plus 4 is 10. Another 4 is 14. So we have 2 more bits left. That means we have 4 entries on the highest level, giving us 3 levels, and we've done this part. In the next step, we take this address B40 and this virtual address here. I want to go for a valid address here, so I will just probe until we have a valid address so that we can go through the full address translation, because the others stop earlier where a valid bit is not set on one of the earlier levels. So we will take this address here and do exactly the same things as before. I didn't want to draw besides the whiteboard. That's not nice. Let me just draw on the whiteboard, and I will put here the address 2A53, and we have the offset. The offset is we have 6 bits, so it's 5-3, but the 4 is not there, so it's 13. Then we have the page table index, which is the next. How many bits do we have there? We can look up and see it's 4 bits, 4 bits, and then 2 bits. So the next 4 bits are the page table index. So it would be A53 shifted to the right by 6, and then we have to make sure that it's only the top, only the 4 bits. So this is the same as shifting this by 2. This means this becomes a 4 and the A becomes 5. And then in the next step, this becomes a 2. This becomes an A. So the PTI is 2A. Just shifted this to the right by 2, 2A. And now we only want 4 bits of that, because we only have 4 bits for our page table entry. That means we can cut off the first part. Next level, the page directory index. Page directory index is at offset. Let's check this again. We have this here. So it's 6 bits, 4 bits. So we have to cut off 10 bits, and then the next 4 bits is the page directory index. So it's 2A53 shifted to the right by 10 bits. That's the same as removing 2 characters and shifting them by 2 bits to the right. That's also working. And then we have here, if we shift this to the right, the A becomes 4, the 2 becomes a 1, and then this is a 2, and the 1 bit goes up here, so it becomes an A. So the next index is again A. Okay, interesting. This is what we call a self-referencing page table. This is a trick that some operating systems use to map page tables into virtual address spaces. And then we have a page directory pointer table index, and that's 2A53 shifted to the right by, we have 6 plus 4 is 10, plus 4 is 14, shifted to the right by 14. Okay. Very nice. So this is the next step. We shift this to the right by 14, and that means the PDPTI. If you take a close look at this, this is 1, 2, 3. This is 12 bits. So this is 2 shifted to the right by 2. This is 0. 2 divided by 4 is 0. Yes. PDPTI is 0, so that makes it very easy. So we can start off at B40. So let's go for null xb B40, and that's here. We take these 4 bytes. So we have this entry here. It's 4D 30, or that's a long entry, 08, and CB. Okay, it can be valid because B has the lowest bit set. The next step is setting all the bits that we don't need to 0. We only need the frame number, the 14 bits there, and we don't need anything of the rest. Okay, let's see. we cut away the lowest 6 bits. That means we can cut away this and still have to shift it to the right by we don't shift. We don't shift yet. We just set it to 0, right? This is already set to 0. Then we have 14 bits which are used, which is 2 bits here and then another 12 bits. So that's up to here, right? So that we have exactly 4 bits plus another 16 bits. That would be 20 bits, yes. And everything above this is set to 0, so we can ignore it. So this is our result here. This is the physical address that we continue at. And the physical page number then would be 8C0 shifted to the right by 6. That's the same as removing the 0 and then shifting this to the right by 2. This becomes a 4 and then a 2, and the C becomes a 3. 23. Let's check whether 23 is correct. Null x23 is not correct. What did we do wrong? Let's check that. PDPTI. Did we compute everything correct? I'm in the wrong line. Ha! Of course. Null x23 is correct. Yes. I was already wondering why everything is wrong. I mean, the advantage of an oral exam here is that the tutor can look at what you do and can try to understand what you do, ask you what you do, and if you do the right steps but just have small computation errors, then it will not have an effect. It will not lead to deduction. But you will have to practice this a lot to be able to convince the tutor that you actually know what you're doing. So the next level, 23. So this is 8C. We continue with this address 8C0 plus A shifted to the left by, and now we have to be careful because before we didn't have to shift because it was 0. 0 doesn't care. But this is 4, so we have to shift it to the left by 2. Shift it to the left by 2. A becomes, this is a 1010, so it becomes a 14, and then it becomes a 28. 28. Okay. C plus 2 is E, and then we have an 8 here. 8E8. Okay, very nice. We got this. And let's see what the entry there is. We should have written here the address that we look up first. So it's B40. And it gave us the result 8C0. This one, let's check what this address gives us. 8 null x8e. And there the offset is 8. So it's 0, 1, 2, 3, 4, 5, 6, 7, 8. So it's, we have to be careful because this is not 2 bytes, but we have to read 4 bytes, right? So this is the first entry in the table. This is the second entry in the table. This is the third entry in the table. Okay, 8, 3, E, 0, 0, 9, F3. It can still be valid because the lowest bit is set, and we remove the ignored bits. So this goes away, this goes away, this goes away, this goes away. The leading zeros, we don't need them. 9F. There are still 2 more ignored bits in this F. So the F becomes a C. So what is left is a 9C. We probably have to extend, so we shouldn't remove the characters at the end because we still need this address. But then we make the physical page number out of that. So it's 9C0 shifted to the right by 6, but that's the same as 9C shifted to the right by 2. And that's the same as the C becomes a 3, and the 9 goes over to the right side 1 bit. So it's then a B and the 8 becomes a 2. So it would be 2b. Let's check whether that's correct. Null x2b. It's not correct. Doesn't like it. Okay, let's check what we did wrong. Maybe I was too fast now with computing this. The page directory index might be wrong. This might be wrong. We could have an error in any offset here. Let's maybe check this one again. Okay, so it's yeah, let's recompute this entire line. Maybe we get to a different result then. I didn't see where the mistake was. So we have 2a53. We have to shift this for the page directory entry by 10 because this was consuming 6 bits, 4 bits, shift it to the right by 10, and then only take the topmost 4 bits. So it's then the same as removing 8 bits. So it's 2a shifted to the right by 2. That's maybe also some information that we want to keep here. Shifted to the right by 2 actually, you know, we have to be careful with keeping this information. The 2 becomes an 8, right? It becomes a 1 and then an 8. So it's 8, 0 plus, and the A had an 8 in there and 2. The 2 is gone. The 8 becomes a 2. So it's 82. That's a completely different index than I had before. What did I do wrong before? Did I not shift? I'm a bit confused now that I had a completely different offset index before. So it would be 82, and of course we only take the lowest bit, so it would be 2 and not A. Maybe we have to recompute these as well. Maybe I did a mistake there as well. So it's not, yeah, it's not as we said before, but it's 8C0 plus 2 shifted to the right, shifted to the left by 2. That means it's 4, it's 8. So it's 8C8. Okay. Probably before I took too many bits or something. Maybe I didn't truncate something. I should have truncated, or maybe I. Yeah, interesting. So let's check whether this one is correct. So it's 0. So it's 0, 4, 8. Let's check. Maybe this one is better. And this one would be C, 4, 5 is set. So we can remove the ignored bits. This one, this one, this one, they are all ignored. This one is not needed. This one, we set it to 0 because we don't care. And this one, only a 4 remains here. So it's 1640 as the next physical address. And if we want to get the physical page number, it would be 1640 shifted to the right by 6. That's the same as 164 shifted to the right by 2. That's the same as 3. That becomes a D. Is that correct? No, it's not correct. So it would be 1011, and that would be a B. Okay, so this becomes a B. Then we have the 4 becomes a 2. So that's the first step. So we have to still shift this to the right by 1. And then this becomes B2 shifted to the right by 1. That's 1. And of course from the B we get another one. So it's 9. And the B gave 1 bit away. So it's A, it's 5, it's 59. That's very, very odd. Oh no, it's fine. It's because it's a physical page number. It can be fine. can be fine. It can be an odd number. Malix 59. Also not correct. We still have a mistake here. Or maybe something is wrong with my exam generator, or maybe I didn't practice this in a long time, and all of these could be reasons why I'm doing this wrong. So if you see the mistake somewhere, please let me know. We are computing the page directory index again, and we already know that this last line was correct. We already have confirmation for that, so the mistake must be up here. We shift this to the right by 10 because we need 10 bits, 4 from the PTI and 6 from the offset. Okay, removing this means shifting this to the right by 2. This is the same as 1, 5 shifted to the right by 1. Ah yeah, we just made a mistake before because we lost this one, I think. Yeah, it must be the case. So, and this is the same as this is 1, 4 plus 1, and this shifted to the right, right? The 1 is gone, and then we still have to shift this one, so it's 2, and the 1 here goes away, so it becomes an A. So A was actually correct in the first round. We had an A there, and that was fully correct. I don't see why what I did wrong here. Okay, so it's an A. Maybe I'm using too many. Am I using too many bits here? No, 23 was correct. A. 8 C 0 plus A shifted to the left by 2 because we have 4 bytes page table entry equals 8. Or we can do this in multiple steps, of course. We first have 1, 4, then it's 2, 8. And then we are exactly where we were before. It was 8, and then not D, but E, 8. 8E8. I looked exactly that one up before. 8E8. Maybe something is wrong with the exam generator right now, because I now have the second example where I think I got it right, but maybe didn't. Maybe I miscopied something. That is also possible, that you copy something wrong onto the whiteboard. 3E0 09F3. It can be valid. We set all the bits to 0 that we don't need, and leading bit zeros we don't need. We set this to 0, we set this one to C, and we get to 9C0. And this one, 9C0, shifted to the right by 6, is the same as 9C shifted to the right by 2. And that's the same as, because we can decompose this into the different components. So this is 1C and 8,0, and C, this one becomes 4 and then a 2, so it becomes a 20, and this one becomes first it becomes an E, and then it becomes a 7, so it's 27. So this one is 27. Okay. Did we do the mistake there before with the computation? I think we didn't have 27 before. 27. Ah, okay. Finally, we got it. Okay, I don't exactly know where I made the mistake before, but for some reason we first had 9C before, and I think we did the last part, the shifting, wrong. We could have just checked this one again. Okay, let's assume we didn't make any more mistakes, so let's just continue with this one on 9C0 plus A shifted to the left by 2, and that would be 9e8, and that gets us to null x 9e8, and that's null here, and then we have this. So it's now the page table entry, so we can directly read things from there. DA5003-1F. Okay, this is valid, and we know that it's valid, executable, writable, and readable. And I again have things wrong. I don't get it. Okay, what did we do wrong here again? So let's see. This one shifted to the right by 6 becomes 2A5 shifted to the right by 2, and this becomes 4, this becomes a 2, this becomes a 5, this becomes a 1. We have to shift it by 1 more, so this becomes a 1, but also gets a 5 from there, so it becomes a 9. And this becomes a 2, and this we don't even care about, because actually this entry must be 9, it seems. That was the mistake. Oh yeah, I introduce a lot of computation mistakes today, a lot more than I usually do. I mean, we already have done these examples in the lecture, and I've also computed them on my own, but I don't know. Okay, 9. So this would be 9C0 plus 9 shifted to the left by 2, and that would be 9 shifted to the left by 1 is 1, 2, and then it becomes 2, 4. So it would be 9E4. Let's look up this address. 9E4. Okay. Here we have another address. Let's see whether this one works. Okay. 17F00363. Okay. Now we can read the bits from there, as it's the page table entry, and hope that this time we got the not another computation mistake in there. We got a lot of them today. So yeah, this is 3. Yes, we already have that page table entry correctly filled in, and the physical page number, we can remove these bits that we don't need again. Okay, this becomes a 4. The topmost bits we don't need, so it's 340. This is the page number. Then if we shift this to the right by 2, the 4 becomes a 1. To the right by 2, by 6 actually. 34 shifted to the right by 2. This becomes 1. And this one becomes a C, which is added on top of that, so it's a D. And so the page ppn must be null xd. That's correct. And then we can add the physical address, and that's null x, not null x 340, because we still have to add the offset, and that's 13, that's 53. Okay, we've solved that example. And for the other one, I will definitely investigate that, and I will post on Discord the solution for the other one. And I will try to figure out where I made the mistake, and then we can also consider the other one solved. Are there any questions? If there are no more questions, then I would end the stream here. We are long over time already, and see you next week for the lecture again, and then it's the last lecture probably. See you.